In this lecture, I want to introduce some basic tools which are useful for dealing with complicated or lengthy sums and products. When you need to add up a small set of numbers, for example, to add up the numbers in the set of integers s consisting of -6, 2, 7, and 121, it's easy to just write -6 plus 2 plus 7 plus 121 equals 124. However, if I ask you to add up all the squares of the natural numbers from 3 to 200, it would be silly and very time-consuming to write out all 198 numbers. We can use dots to represent the statement continue in the obvious manner, so we could write out this sum as 3 squared plus 4 squared plus 5 squared plus ... plus 198 squared plus 199 squared plus 200 squared. However, we have an even better and more precise method for representing such a sum. We use a capital Greek sigma to stand for the command add up the numbers defined by the formula which follows. And we use sub and superscripts attached to this sigma to explain which range of numbers we want to add. For the sum of the squares of the natural numbers from 3 to 200, we write capital sigma with a subscript k equal 3, superscript 200, and then after the sigma we write k squared to show what we're adding. And this stands for the command add up the numbers k squared starting with k equal 3 and ending with k equal 200. So that compact expression stands for the very long sum 3 squared plus 4 squared plus ... up to 200 squared, as we wrote before. You can see that summation notation makes things nice and compact. The other thing to notice is that the summation index k is a dummy variable which runs through a subset of the integers beginning with the lower limit of the sum and ending at the upper limit of the sum. The particular symbol we use is not important. We could just as well have used J or T or even George to indicate the summation index. The summation from k equal 3 to 200 of k squared is exactly the same as the summation from j equal 3 to 200 of j squared, and that's the same as the summation from t equal 3 to 200 of t squared, and that's the same as the summation from 3 to 200 of George squared. In computer programming, a dummy variable is often called an internal variable, meaning it is only used in an internal subprogram and then disappears. Let's look at some more simple examples. The summation from I equal 1 to 4 of the sine of I times pi over 2. Well, that's the sine of 1 times pi over 2 plus the sine of 2 times pi over 2 plus the sine of 3 times pi over 2 plus the sine of 4 times pi over 2. Now you've reached the upper limit and you stop. You calculate each of these, and the sum turns out to be 0. Let's look at another example. The summation from k equal -2 to 3 of the ratio of k minus 1 to 1 plus k squared. You set k equal to -2, the lower limit where you start, and you calculate that ratio and you get -3/5. You increase k by 1 from -2 to -1, and you calculate the ratio and you get -2 over 2. Now you continue in this way. The next term would be with k equal to 0, where you get -1 over 1. And the next term would be k equal to 1, where you get 0 over 2. And you end up finally with k equal 3, where you calculate the ratio as 2 over 10. So, makes perfectly good sense. We just have to carry it out in order, and we get the final result. And if we are given a set S, for example, the set of integers that we had before, S equals -6, 2, 7, and 121, then we can represent the sum of the elements by writing sigma A, with the subscript A belongs to S to show which A's we're talking about. Again, a very compact notation. We have a similar notation for products using the capital Greek letter pi to stand for the command take the product. For example, the product of the elements in our set S above is written product of A, and S, which is the product minus 6 times 2 times 7 times 121, and that works out to be minus 10,164. The product of all of the squares of the natural numbers between 3 and 200 can be written very compactly. It's the product starting at k equals 3 and stopping when k is 200 of k squared. And that's just 3 squared times 4 squared times 5 squared and so on up to 200 squared. And I really don't want to write down that actual number, but since you're probably curious, it is as follows, and no, I'm not going to read it out. I hope you are surprised by the size of this simple-looking expression. It is our wonderfully efficient notation that makes this huge number easy to write down and manipulate. Here's another example of our product notation in action. Take the product starting with j equal 1 and stopping when j is 5 of 2j divided by 2j plus 1. And what you get is, in the numerator, the product of all the even numbers from 2 to 10 divided by the product of all the odd numbers from 3 through 11. As you can see, the notation considerably simplifies writing down mathematical expressions, even if the actual calculation is still a handful. One very special product is the product of all of the natural numbers from 1 up to a given natural number n. This is written n followed by an exclamation point and called n factorial. For example, 1 factorial is 1, 2 factorial is the product of the numbers 1 and 2, that's 2. 3 factorial is the product of the numbers 1, 2, and 3, which is 6. 4 factorial is the product of the natural numbers from 1 to 4, which is 24, and so on. And notice that 6 factorial, for example, is just 5 factorial times 6. So if we've already calculated 5 factorial is 120, then 6 factorial is 6 times 120 equals 720. Factorials get large very quickly. You can use your calculator or a computer to verify that 7 factorial is 5,040, and 15 factorial is 1.307674368 times 10 to the 12th. There are a few small tricks to learn for those not accustomed to summation and product notation. It is a universal convention, for example, to define 0 factorial to be 1. This seems really strange, but it turns out to be perfectly natural when one studies a factorial function in depth. A second point. The sum from k equal 1 to 12 of the number 2 means add up the number 2, starting with k equal 1 and ending when k is 12. So you get 2 plus 2 plus 2 exactly 12 times. In other words, 2 times 12 is 24. This applies to any constant c being added up any number of times. The sum from j equal 1 to n of the constant c is n times c. A third point. There is nothing sacred about the beginning value of the summation index. In our examples, we generally began at the value 1 for simplicity, but we can begin at any integer, increasing the value by 1 for each additional term, until we arrive at the upper limit of the sum or product. For example, the sum from j equal minus 2 to 4 of j plus 3. Well, you just write it out and you get 27. The product from j equal minus 2 to 4 of j plus 3. Again, you just write it out, minus 2 plus 3, minus 1 plus 3, 0 plus 3, and take the product of all these numbers, and you get 5040. In addition, both upper and lower limit can be negative. For example, you can take the sum from k equal minus 5 to k equals minus 2 of the numbers 2k plus 5. You just start with k equal minus 5. That means that 2k plus 5 starts at minus 10 plus 5. And then you move up k to minus 4, and then to minus 3, and then to minus 2, and you stop. And then you add up these numbers, you get minus 8. In the same way, the product of the numbers from minus 5 to minus 2 of 2k plus 5 is the same thing, only now we take the product. We start with k equal minus 5, and we get 2k plus 5 is minus 10 plus 5. Then we move k up to minus 4, and we get minus 8 plus 5, and so on. And we stop when k gets to minus 2. And that product turns out to be minus 15. A fourth point. We can use the field properties of the real numbers to simplify calculations. For example, suppose that you have already calculated the sum from k equal 1 to 11 of k. That's just 1 plus 2 plus 3 and so on up through 11, and it's 66. Now you want to calculate the sum from k equal 1 to 11 of the numbers 3k plus 4. Now you can write that out. It's 7 plus 10 plus 13, and you stop when you get to 37. But by the algebraic properties of the real numbers, you can first take this sum apart, which corresponds to the idea of regrouping a sum. So in this case, you get the sum from k equal 1 to 11 of 3k plus the sum from k equal 1 to 11 of the number 4. Then we can factor out the 3 from the first sum. So we get 3 times the sum from k equal 1 to 11 of k, plus the sum from k equal 1 to 11 of 4, which is just 4 times 11. We already know the sum from k equal 1 to 11 of k is 66, so this ends up becoming 3 times 66 plus 44 equals 242. Much quicker than adding up the original numbers. A fifth point. We can shift the index in a sum or product without changing its values. For example, if I add up the numbers k minus 2 quantity squared, starting with k equal 3 and stopping at k equal 10, what I get then is 1 squared plus 2 squared plus 3 squared, and I stop when k is 10, and that's when k minus 2 is 8, so I stop at 8 squared. So all I'm doing is adding up the numbers j squared from j equal 1 to 8. The connection between these two is the index shift, defined by j equals k minus 2. So you start with the sum from k equal 3 to 10 of k minus 2 quantity squared. And then you define the index shift, j equal k minus 2. So you will be summing j squared instead of k minus 2 squared. But you must adjust the limits to account for the change in the summation notation. The lower limit, k equal 3, corresponds to j equal k minus 2 equal 1. And the upper limit, k equal 10, corresponds to j equal k minus 2 equal to 8. So the sum will be the same if we write it in terms of the new summation index as the sum from j equal 1 to 8 of j squared. We have a set of formulas for certain sums of powers of natural numbers. If we add up the number k, starting with k equal 1 and stopping when k is n, that's the same as taking the product n times n plus 1 and dividing by 2. And we have a similar formula for the sum of the squares. The sum from k equal 1 to n of k squared is the product n times n plus 1 times 2n plus 1, all divided by 6. And yes, we can continue indefinitely. We can sum k cubed from k equal 1 to n. We have a formula for that, and so on. We'll discuss proofs of these formulas later on, but here I want to focus on simple examples of the use of these formulas. For example, the sum from k equal 1 to 100 of k is just 100 times 101 over 2, which is 50/50. The sum from k equal 1 to 9,050 of k is 90/50 times 90/51 over 2, which is a big number, as you can see. The sum of the squares, j squared, from j equal 1 to 103 is the product 103 times 104 times 207 over 6, which is 369,564. In each case, this calculation took a few seconds using a simple hand calculator. Now suppose that some perverse person wants you to add up the numbers p minus 2 quantity squared, starting with p equal 3 and stopping when p is 100. Well, you just shift the index by defining j equal p minus 2, and your sum becomes the sum from j equals 1 to 98 of j squared. And by our formula, that's 318,549. And again, there is nothing sacred about a lower limit of 1 for the summation index. For example, the sum from k equal 3 to 100 of k is the same as the sum from k equal 1 to 100 of k minus 1 minus 2. In other words, take off the first two terms. And that's the product, 100 times 101 over 2, minus 1 minus 2, which is 5047. Similarly, the sum from k equal 4 to 100 of k squared is the same as the sum from k equal 1 to 100 of k squared if you subtract away the first three terms. So you subtract 1 squared, 2 squared, and 3 squared from that sum. So you get by our formula the product 100 times 101 times 201 all over 6 with, subtracted away from it, 1, 4, and 9. Next, I'd like to systematize the arithmetic laws for expressions involving summation and product notation. We know that in ordinary algebra we can factor out a common term from a sum. For example, 2x plus 2 is twice the quantity x plus 1. And 3x squared minus 6x plus 15 is 3 times the quantity x squared minus 2x plus 5. This is just the distributive law in operation. Of course, it applies to any sum. If I'm given the sum from k equal 1 to n of 2k, then I can factor out the 2 and write that as twice the sum from k equal 1 to n of k. And if I'm given the sum from k equal 1 to n of 3k squared plus 6k plus 15, I can factor out the 3 and write that as 3 times the sum from k equal 1 to n of k squared plus 2k plus 5. In general, if you are given a set of numbers a1, a2 up to an and a constant c, then the sum of the products c times ak, starting with k equal 1 and ending with k equal n, is c times the sum of the numbers ak. With products, things are a bit wilder. If you have the product k equal 1 to n of twice k, then that's 2 times 1 times 2 times 2 times 2 times 3, and so on up to 2 times n. So there is a factor of 2 in every single one of your terms in your product, which means that the product k equal 1 to n of 2k is 2 to the nth times the product from k equal 1 to n of k, and that's of course the same as 2 to the nth times n factorial. The moral is, use common sense. We can also regroup sums and products. For example, for the following sum, summation k equal 1 to n, 3k plus 5, we can take that apart as summation k equal 1 to n of 3k plus summation k equal 1 to n of 5. And that's 3 times summation k from 1 to n plus summation 5 from 1 to n. And that's the same as 3 times, from our formula, n times n plus 1 over 2, plus 5 times n. Here is what we did, but in slow motion. In general, if you are given two sets of numbers, a1, a2 up to an, and b1, b2 up to bn, and two constants, c and d, then the sum of the expression c times ak plus d times bk, starting with k equal 1 and stopping when k equals n, is the same as the sum k equal 1 to n of c times ak plus the sum from k equal 1 to n of d times bk, and then you can factor out the c and the d from the resulting sums. For our last topic in this lecture, I want to discuss the special Riemann sums presented in the text material. I won't go into as much detail as the text, but will focus more on providing some background and motivation. When we take up the study of the problem of finding the area under the graph of a curve, we are going to use a large number of very narrow rectangles to approximate that area. For example, consider the parabola y equals x squared. And suppose you wanted to find the area under this curve and above the interval 0, 2. What we will do is divide the interval 0, 2 into n equal subintervals, each of length 2 over n. The picture shows the case n equals 6. Over every subinterval, we draw a rectangle. For the height of that rectangle, we're going to arbitrarily choose the height of the parabola, that is its y value, at the right endpoint of the subinterval. Now we need to do a careful calculation because we need the x-coordinate of the right endpoint of each of those intervals. If you look at the picture, you'll see that the right endpoints are just the points j times 2 over n, where j can be 1 or 2 or 3 and so on, up to j equals n. Notice that j equal n gives you xn equals 2. Then the heights of the n rectangles are given by h1 is x1 squared, which is 1 times 2 over n squared, and that's just 4 over n squared. h2 is x2 squared, and so on. And hn is xn squared. Now that we know the heights, we notice that the base of every rectangle is, of course, 2 over n. So the area under the graph can be approximated by the sum of the areas of the rectangles. The area under the graph is approximately 2 over n times the square of 2 over n, that's x1 squared, plus 2 over n times the square of twice 2 over n, plus 2 over n times the square of x3, which is 3 times 2 over n, and so on. And you can write that out in summation notation as the sum from j equal 1 to n of 2 over n times the quantity j times 2 over n squared. And when you clean that up, that's just 8 over n cubed times the sum from j equal 1 to n of j squared. And this last sum is one of the basic Riemann sums. When we approximate the area under a graph by this process of subdivision using areas of rectangles, the resulting sum is called a Riemann sum in honor of Bernard Riemann. In the 1840s, he founded the modern theory of finding area, and we will see much more of his work later on. For now, let's just illustrate how easily we can approximate the area under the graph of y equals x squared by choosing a large number of rectangles. We ended up with a very simple formula. The area is approximately 8 over n cubed times the sum from j equal 1 to n of j squared. And we have a formula for that sum. And when we use that formula and clean things up, we get the area is approximately the ratio 4 times n plus 1 times 2n plus 1 divided by 3n squared. So we have reduced this complicated approximation process to the calculation of a simple arithmetic formula for any value of n. Another example of the power of abstract mathematics. Here are the results for various values of n. If you choose n equal to 10, I get that the area is approximately 3.08. Well, that's probably pretty crude. Let's try n equal 100. We plug it in, we get the area is approximately 2.7068. Now we try n equals 1,000. That's a lot of rectangles. But it's easy to write down the formula. The area is approximately 2.670668. And let's not be shy. Let's go up to n equal 10,000. It's really not that much more difficult with this simple formula. For n equal 10,000, we get that the area is approximately 2.667 and a bunch of other decimals. So we seem to be homing in on the true area with very little effort, thanks to this beautiful summation formula.